Hello everyone, today I'm just going to explain to you why the Falcon 9 rockets, and also other rockets, don't follow an exact gravity turn. Now the gravity turn is a well-known, somewhat ideal rocket flight path. The idea is that you launch vertically, of course, then at some relatively early point, relatively low, somewhere at 1 kilometer or 3 kilometer or something, you start turning from the vertical position by a few degrees to something like 85 degrees pitch, so you're 5 degrees away from the 90-degree position, and then after a while your flight direction will have essentially shifted a little bit along with that direction, and then you basically just go prograde. You keep the rocket lined up with its direction of flight, keep burning prograde, keep it basically aerodynamically stable, or and let gravity do the turnover. And of course you optimize how far you pitch over, when you pitch over, how much thrust you apply to optimize your path through the atmosphere, and that is supposed to be a relatively efficient path. And there's a mathematical reason for this, because of the conservation of energy and the fact that power equals force times speed, or energy equals force times raise. So applying thrust in the direction of travel is usually a more efficient way to add energy, add potential and kinetic energy to your vehicle than to thrust diagonal to your direction of travel. However, this doesn't really accommodate for other effects that are more important, but then the gravity turn does also follow a quite reasonable trajectory through the lower, vertically through the lower atmosphere, and then starts turning sideways relatively soon, and then if you plan it right, turns exactly sideways as you reach orbit. So it does work relatively well. It's not really perfect mathematically. It is perfect in terms of energetics, assuming a vacuum, but it's close enough, and so it's often used as an approximation for first designs, but then for several reasons most rockets slightly deviate from it. And this depends on the rocket design. Some rockets are very close to it, some deviate really far from it, which has several reasons. One is just that it is not perfectly efficient. It is energetically efficient as you thrust in the direction of travel, but then you must take into account the changing atmospheric density and trigonometric effects when it comes to delta V adding up, and so overall it's not perfect. Also, there are other concerns like safety, atmospheric pressure, so dynamic pressure acting on the rocket. You might want to minimize that because your rocket is just not very sturdy. Then for safety reasons you might want to minimize dynamic pressure and thus want to get out of the atmosphere relatively quickly at a relatively low speed and only then start turning. There are also reasons like weird rocket designs where you have a very variable thrust weight ratio because you have few stages, and so it burns up fuel, gets a really high thrust weight ratio, then stages and gets a really low thrust weight ratio again. And there are other features like reusability, and that's why on many flights the Falcon 9 doesn't do a perfect gravity turn, because reusing the first stage gets easier if you start relatively steep. And so the Falcon 9 starts in a rather steep gravity turn. It does actually follow a close gravity turn trajectory, just not one optimized for the orbit it's actually going to in the beginning. So it starts off as a gravity turn, then as it reaches some altitude shortly before staging, and then during and after staging, it turns quicker than a gravity turn, and then after staging it goes on flattening out its trajectory and follows a much less steep gravity turn. So it's basically two gravity turn pieces patched together at the point around staging by a phase of below gravity turn pitch. This is because landing and reusing the first stage gets easier if it goes mostly up and straight down again and less sideways. If you have less sideways way in your first stage burn, that means that if you land on a drone ship, the drone ship doesn't have so far out on the sea. And if you fly back to Cape Canaveral, which is mostly when the Falcon 9 does a really great deviation from a gravity turn, then all the lateral speed you build up during the first stage burn, you have to not only cancel out, but also go backwards during the boost back burn, while the vertical speed you build up during your first stage burn, that's just gonna be cancelled out by gravity over time, and then through gravity and aerodynamic drag, you're basically gonna come down where you started. So it's more optimal in terms of fuel for a reusable rocket to start off with a relatively steep trajectory, then around staging have a phase of below gravity turn pitch and then follow a different gravity turn into orbit. You could observe something opposite with the space shuttle. The space shuttle had a very variant thrust weight ratio, as it was a sort of early 1.5 stage design. It also had a weird thrust angle because it was asymmetric and its center of mass wasn't really lined up with its center of thrust, and so they used gimbal to counter that, and so they had angled thrust. And what the space shuttle did was actually start with a really flat gravity turn. Actually, it started by going straight up for quite a while, then started a late gravity turn, but a really flat one, and then kept its pitch slightly above gravity turn for a while in order to actually make it to orbit. Other rockets often deviate from a gravity turn trajectory because of their control systems, because of gimbal control, for example, which means that the rocket would slightly shift into the opposite direction of your turn while you start your turn. And of course, there are all sorts of weird exceptions and special reasons why to deviate from such a trajectory, including hypothetical concepts like space planes, of course, that would follow a completely different trajectory in order to utilize the lift of their wings. And some rockets have to fly a somewhat swiveling trajectory on their launch in order to avoid unclear areas. For example, we know that the US launchers mostly launch out over the ocean in order to avoid any falling debris from hitting any civilized areas, and some countries just don't have that practically located launch sites, and in order to prevent political turmoil, they have to essentially dodge a critical area. So their rockets have to launch on a wrong inclination at first and then adjust their inclination in order to launch into a certain orbit, because if they just launched straight into the correct inclination, they would fly over areas that they don't want to fly over. Anyway, I hope you enjoyed this little explanation. Maybe you better understand now why the Falcon 9 launches, especially the ones landing back at Cape Canaveral and the flight animations, tend to look a little bit weird if you're used to other rocket launches, or why the space shuttle launched so relatively flat compared to other rockets. And as always, thanks for watching.